So we're now on the last topic for midterm, which is crystallization. We only have two topics here for now. That's evaporation and crystallization. So when we speak of crystallization, the main goal or objective is in the formation of solid particles within a homogeneous phase. So the solution is concentrated and usually cooled until the solute concentration becomes greater than its solubility at that given temperature. Then what happens? The solute comes out of the solution, forming crystals of pure solute. Now, it could also be viewed as a solid-liquid separation process in which mass transfer of a solute from a liquid solution to a pure solid crystalline phase occurs. So it's a solid-liquid separation process. Now, crystallization may occur in the case of the formation of solid from vapor, and that is in the case of the snow, but we don't have it here. And it could also be occurring part as the solidification, and most of the time the solidification from a liquid melt. And this is usually happening in the manufacture of large single crystals. In the industry, we have crystallization from liquid solution. So we're forming crystals from a homogenized liquid solution. Now, in crystallization, we are not only interested in the yield and the purity, yield meaning the quantity and the purity of the crystals, but we are also concerned this time with their sizes and the shapes. The size uniformity is really desired so as to minimize caking in the package. I think you understand what caking is. Also for ease in pouring, and for ease in washing and filtering, and for uniform behavior whenever they are used already. So the reason why we add up to yield and purity in crystallization, the desired size and shapes of the crystal, it's because of these very important factors. Most important of this is the caking, which will be a big deal of a problem to deal with if in the packaging already of the powdered form of the crystal, we have a problem with the ununiform size and shapes of the solid produced. So it will be forming into cakes or lumps. And of course, it would be hard in terms of its behavior during pouring. It would be hard. Now, what about crystals? So these are solids composed of atoms, ions, or molecules which are arranged in an orderly and repetitive manner. I think this was defined in your material science then. Highly organized type of material. We know that its structure is organized and it's really having a specific pattern. Now, it could also be defined as atoms, ions, or molecules which are located in three-dimensional arrays or space lattices. Now, these may appear as polyhedrons having flat faces and sharp corners. So if you could recall your material science, you even studied the different shapes of these particular crystals, depending on these particular faces that they have and how many sharp corners they have also. The angles between the corresponding faces of all crystals of the same material are equal and are characteristic of that particular material. And as such, we say it's an organized arrangement of atoms, ions, or molecules. Now, when we form crystals in the industry, we have this what we call magma. These are terms now that we encounter when we process the particular crystal from a solid melt, or if it is to be taken out from a solid melt. So in industrial crystallization from solution, it is the two-phase mixture of mother liquor and crystals of all sizes which occupies the crystallizer and is withdrawn as the product. So we refer to as that particular solution consisting of the mother liquor and the crystals as the magma. So the magma is the one that is being processed by your crystallizer, and afterwards, in the case, for example, of the sugar industry, this particular magma is separated into sugar crystals and molasses in the centrifuge. So the solids now are separated from the, shall we say, the byproduct, which is molasses, in the process of centrifuging. So now the clear sugar crystals are separated from the liquid. Now, here's a particular schematic diagram for the formation of crystals in the process of crystallization. So we have the feed introduced into the crystallizer. The crystallizer is undergoing cooling, or there's the cooling of the feed inside the crystallizer so as to initiate the growth of the crystal. So the crystallizer here is viewed as a heat exchanger wherein we have cooling water introduced to it. Now, in the process, the crystallizer later on will have a product dispensed in the form of magma, which is separated further into the mother liquor and the crystals. In the case of crystallization, we are interested with the crystals, although the mother liquor can still be processed. Now, another schematic diagram is that in the case of vacuum crystallizations, it's actually similar, very similar to that of the simple cooling, but this time we have already the vapor being produced in the crystallizer. So in order to solidify or to initiate growth of crystals in the crystallizer, it is being concentrated. And how is it being concentrated? Vapor or water is being removed from it in the form of gas. That way, it will reach as a condition of what we call supersaturation. If it reaches the condition of supersaturation, then it will now be a condition wherein growth of crystals will be starting, or solids will try to precipitate out from the solution. In that case, we have already the magma. And then we can separate now the two, the crystals and the mother liquor, wherein we're more interested again with the crystals. Now, as to industrial applications of crystallization, so crystallization is used for the production, purification, and recovery of solids. Most of the time, it's in the recovery of solids and production. Now, at times, it's also used in purifying a particular, shall I say, solid which has impurities present on it. So one way of separating the impurities from the component in the solid that we are interested in is in the process of crystallization. Now we can also have powder salt production, but this time we're not using any industrial equipment, and we have in this case the salt farming in Las Piñas. So this is how they do salt farming. There is this, shall I say, daw sa aton lingwahe daw puno nga type. They put, shall I say, some form of restriction for seawater to keep on flowing, and in the manner of the seawater being evaporated, these particular salts are formed. So they solidify out of the seawater that has been restricted only in a particular portion. So this does not need any equipment. But in the industry, so we have this particular a simple example of a tank crystallizer that is also used in salt production. But it's not only salts that are produced in the process of crystallization. We even have our own very own sugar industry. So the sugar production is using crystallization of the solid sugar from what we call as the masikwet. We call it in the sugar central the masikwet, the mixture of the mother liquor and the crystal. So later on, they will be separated into molasses and the sugar crystals. So in the case of sugar crystal production, we have this what we call liquid evaporator crystallizer. An evaporator that at the same time functions as a crystallizer. And in our language, we call it, when you go to your OJT later on in Sugar Centrals, we call it the tatso. They call it the tatso. And the operators are called panmans. So they concentrate the juice, the cane juice inside the evaporator, and it goes beyond concentrating. So in that particular evaporator, crystals are also being formed. So it's before, in my time, I used to work in the sugar central. Before, they do it manually. They pull a certain amount of, or they take a sample of the, shall I say, the magma inside the evaporator through a particular, shall I say, sample stick. And then what they do, they put it on a crystal, and then ang ginaubras ang mga panman, gina-site-site na nila, ka ginatanaw-tanaw kung may crystals na nga nag-form or wala. And they are really very experienced in that, more experienced than any computer system then. They do it very manually. And when they say this is okay, then that's the time that they will dispense the masiquet inside the evaporator crystallizer down to the crystallizer below. So in Sugar Central, the crystallizer is just a simple cylindrical tank, semi-cylindrical tank. So tunga na siya sang tangke nga laba-laba, and it has cooling coils that continually rotates and homogenizes the, shall I say, the masiquet being dispensed by from this evaporator. So in the process, the initial growth of the crystals initiated in the evaporator crystallizer are further enhanced because of the cooling process. After the crystallizer, which is usually situated below the vacuum pans, we call them the vacuum pans, it's being directed to the centrifuge, where they are now separated into molasses and sugar. After the centrifuge, it goes to bagging already for the warehouse, for selling, for marketing. So that's how sugar is being produced here. Now, this one is for those who are majoring in ECE or computer. Of course, everything now is dependent on this silicon wafer, where everything in our gadget, in our home appliances, refrigerator, freezers, everything, they have these microchips made of silicon crystals. Or shall I say, they are crystal wafer. So how are these formed? So actually, they came from silicon, okay? Melted silicon. Now, how is this wafer produced? So this is the process of the production of the wafer, okay? So melting, seed crystals, and this is already your wafer. So you have here the melting of the polysilicon, we call it, and then the doping. The doping is a process of introducing some impurity in the pure silicon. That way it will be electrically charged, because pure silicon, class, if you have learned, is non-conductive. So there has to be certain amount of impurity present on it so that it will be electrically conductive. So that's a process of doping. Daw kung wa daw gibutangan mo gid siya hungod impurity para maging electrically charged siya. Then once the melting process and the doping process is done, we have the introduction of the seed crystal. In here, in the animation that you are seeing, that's the tip that goes down. That's the introduction of the seed crystal. That is where the rest of the crystals from the melted polysilicon will grow. So that's your seed. Then you have the pooling, the crystal pooling. This one, that's the crystal pooling already. So you have the beginning of the crystal formation growth when the seed is already lowered down on the melted pool of silicon. Then we have the formed crystal with residue of melted silicon. Now I have more detailed video here. You need not really hear the, shall I say, the audio, because there's no audio, but there's an explanation in the video. So I'd like you to look at it just in time for us to end and then reconnect later. Okay, so that's how the electronics, the chips that we have in our gadgets, in our appliances, in our even our cars came about from the molten silicon that underwent crystallization and then turned into crystal wafers. Now we also have in nanotechnology the application of crystals. Now, this device actually transfers energy from nano-thin layers of quantum wells. These are your nano-thin layers of quantum wells. So there's a corresponding potential difference in these quantum wells, causing the nanocrystals that were placed above to emit visible light. So this is crystallization, shall I say, intermingled or mixed with nanotechnology, or how crystallization was used also in nanotechnology. So those are just few of the many applications of crystallization in the industry. Now we go to industrial crystallization, wherein we're really going to look into the different crystallizers or equipment where crystallization uh, being uh, is happening rather. So we are to look into in industrial crystallization in the diversity and the size of crystals that are being produced during crystallization. So many physical, chemical, mechanical, and even rheological properties of solid materials depend on the grain size and shape. That is why we add this to the size and the shape in the quantity and in the purity as objective in the production of crystals. The examples are pigments of paintings wherein we have titanium oxide crystals. In the catalysts that are used in the industries, they are also formed from crystals, or they are crystal in form. Pharmaceuticals, food products, and materials for electronics, which you just saw a while ago. So the particle size, distribution, and the particle shape of the solid product are essential criteria for its commercial quality. So to this aim, it is necessary to define and perform the necessary physico-chemical transformation and the design of the reactor that will facilitate the process, and then the operating conditions. So all of this has to be monitored closely. That way, the size of the crystal and their shape has to be as much as possible very near to uniform. Now, in crystallization, we have to understand that there is this what we call saturated solution, and there is this what we call super saturated solution. So when we speak of the saturated solution, it's a solution that is in thermodynamic equilibrium with the solid phase of its solute at a given temperature. And since it says here that it's in thermodynamic equilibrium with its solid phase, the solid phase will never precipitate out from the solution because they're said to be at equilibrium. And this is in the condition of saturation. What about supersaturation? So in here, a solution containing more dissolved solute than that given by the equilibrium saturation value at the given condition. Meaning, this is a condition wherein your solution has more solids than it should contain at a given condition at what we call equilibrium. That is the case, our solution is said to be supersaturated. If it's super saturated already, then that's when growth of crystals commence. Now, there are several ways of expressing the concentration of our solution, and that is in terms of degree of supersaturation. In Colson, I took this from Colson, it's represented as delta C, where delta C is equal to C minus C asterisk. Now, this C is the solution concentration, and the C asterisk is the equilibrium saturation value. If you're going to look at it, the degree of supersaturation is simply a measure of how much your current condition of saturation uh, went beyond the equilibrium saturation value. Why? Because you're taking the difference of the current concentration of your solution from the equilibrium saturation value. So it went beyond that particular equilibrium saturation value. How much was that is the degree of supersaturation of your solution. Now, there is also another way of expressing the degree of saturation of your solution, and that is in the case of supersaturation ratio. The supersaturation ratio this time does not get the difference between the concentration at equilibrium and the current concentration, but rather the current concentration is measured in terms of percentage compared to that of the equilibrium value. So your current concentration divided by the equilibrium saturation value is the degree of supersaturation, or shall I say it's just the supersaturation ratio represented as S. Okay, these are ways of expressing your state of your solution. And there's another one, and that's the relative supersaturation, represented by this symbol. I think this is phi. So you know the two, if you know already these two, the degree of supersaturation and the supersaturation ratio, you'll be able to get the relative supersaturation. So your delta C divided by your C asterisk will be your relative supersaturation, or your degree of supersaturation S, if you subtract 1 from it, that would be your relative supersaturation value or relative supersaturation. Now, there's a note here that solution concentrations may be expressed as, so the C's that you are seeing here, the C asterisk, the C, and of course the delta C, which is dependent on the two, can be expressed as mass of the anhydrate over the mass of the solvent, meaning the mass of the solid without the water over the mass of the solid